Hello everyone, I'm Hongpeng. Today I will talk about our work, CrossRoI, cross-camera region of interest optimization for efficient real-time video analytics at scale. This is a joint work of the University of Illinois and George Mason University. And the authors include me, Shuochao, Zhe, Qian, and Professor Clara Nestedt. Recently, surveillance cameras are pervasively deployed in city scale for public good and community safety. At the same time, the rapid development of machine learning and computer vision models enable more advanced tools for surveillance video analytics. Some applications include vehicle detection, vehicle tracking, and beyond. Here is a figure of the traffic cameras deployed in the New York City. As a large number of cameras are deployed, tremendous data are being generated and to be analyzed in every second in real time. This figure presents a general pipeline for real-time video analytics. As the cameras are not equipped with strong computational power, they will stream video clips to a remote server for advanced machine learning-based processing. The processing result can then be used to answer queries such as vehicle detection and pedestrian tracking. However, such application scenario suffers severe resource-intensive problem. And the resource-intensive problem can be categorized into two parts. First is the high network demands for video streaming. The second is the high computational demands for CNN-based inference. These two issues will cause severe challenges to scale the video analytics applications. Multiple solutions have been proposed to solve the resource-intensive problem. The first two types of such solution include frame filtering and resolution configuring. The frame filtering solution will only send frames to the server when significant scene changes have happened. The resolution configuring solution will crop the video frames into small pieces and only encode the very high interesting area with high quality. While these two solutions can reduce the network and computational demands efficiently, they only try to optimize the resource for independent cameras and fail to further reduce the resource demands based on the cross-camera data correlation. The third solution is camera scheduling, which considers the cross-camera data association and choose the best camera at each time to track the target object, other than using all possible cameras. However, this solution only focuses on a few predefined target objects and fail to cover the whole scene comprehensively. Therefore, in this work, we present CrossRoI, which exploits the video content association and redundancy across a fleet of closely located cameras, and to greatly reduce the communication and computational costs in the real-time video analytics framework. As the figure shows, CrossRoI removes the repeated appearance of the same objects in multiple cameras smartly, without harming the comprehensive coverage of the scene. So just as this figure shows, the same car appeared twice from two different views. Therefore, we can confidently remove the left bottom corner of the second view, and it will not harm the comprehensive coverage of any object in this scene. And actually, a lot of surveillance queries can be efficiently answered with only one detection of the target at a time. And some of such applications include vehicle detection, pedestrian localization, and car counting. Based on this motivation, we designed CrossRoI to significantly reduce the resource demands by removing the repeating areas across different cameras. To exploit the cross-camera content correlation and redundancy, we face the following three challenges. First, how to establish cross-camera data association and how to find the repeating areas across different cameras. Second, how to reduce the data intensity with the established cross-camera correlation. And finally, how to best transform the reduced video data into network and computational resource reduction. To solve the above three challenges, we propose the following three corresponding answers. So first, we use object re-identification and statistical filters to establish the cross-camera correlation. And second, we generate optimized region of interest masks for each camera based on a combinatorial optimization problem. And finally, we specially design video compression algorithms and CNN kernels to work with the ROI masks to further reduce the communication and computational costs. Putting all the designs together, we will present the system of CrossRoI. And in this talk, I will mainly talk about the first two contributions of our work, and more details about our third contribution can be found in our paper. Here is an overview of CrossRoI workflow. CrossRoI operates in two phases, an offline phase to learn and establish the cross-camera data correlation, and an online phase to exploit this correlation to reduce communication and computational costs. Here is an overview of the offline phase. The camera first sends a few synchronized video clips to the server. The server collects the video clips and runs reality algorithm on it. After profiling and learning, the server establishes the cross-camera correlation and generates optimized CrossRoI masks for each camera. These ROI masks will be sent back to the camera for later use in the online phase. In the online phase, the cameras are cropped. The cameras will crop their video streams according to the ROI masks, and then send the cropped video to the server for processing. After the video feeds going through the CNN model, the query answer can be achieved. As the video data is greatly cropped, a lot of network and computational costs can be saved. After the CrossRoI overview, let's see some detailed challenge of CrossRoI design. In CrossRoI, we use object re-ID method to establish the cross-camera data association. When a single object appears on two different cameras and generates two bounding boxes, we know that there are data associations between the two bounding boxes area from two different cameras. However, there is a severe problem preventing us directly applying the re-ID bounding boxes. And the reason is that the re-ID results are not perfectly accurate. The re-ID algorithm may identify two different vehicles as the same or fail to recognize the same car from two different point of views. To best utilize the error-prone re-ID results, we studied the pairwise relation between two cameras to learn where and how the re-ID algorithms make mistakes. As this figure shows, we studied the correlation between camera C1 and C2. If an object in C1 also appears in C2, we say this detection is positive. Otherwise, we say it is negative. So all the detection in C1 can be further categorized into the following four cases. So as this figure shows, if all the re-ID results are correct, then the presented bounding box will become true positive and true negative. If a negative object is recognized as another vehicle and thus marked as positive, then this identification will become false positive. Similarly, if a re-ID algorithm fails to recognize the same object across two different views, it will generate a false negative data sample, as this figure shows. We ran the re-ID algorithms across five cameras pairwisely and compare it to the ground truth. And finally, we got the following table showing the performance of the raw reality algorithm. As you can see, the raw reality results generate significant number of errors. However, we have two very important observations help us to use the error-prone reality results smartly. First, the first observation is that the number of true samples is usually significantly large than that of the false samples. For example, the true positive sample is usually greatly larger than the number of false positive numbers, and the true negative sample numbers is usually greatly larger than that of false negative numbers. Secondly, the cross-camera association have some intrinsic physical correlations. That is, if you consider an area in camera 1 always project to a specific another area in camera 2, then if an outlier data sample projects to some other area in camera 2, in this case, we have high probability to say this data sample is very likely to be a false data sample. Based on the above observations, we designed two statistical filters to select a group of high-confidence reality results. We first pass the positive reality samples through a regression filter to remove all the false positive data points. And then we pass all the remaining data through an SVM filter to remove the false negative samples. After the two statistical filters, we will get a high-confidence reality results and can be further used to establish the cross-camera correlations. So after we obtain the high-quality reality results, we can apply this reality data to establish cross-camera correlations. We first divide the frames into tiles and then associate each object detection with the tiles. As the figure shows, the frame is divided into 24 tiles, and the blue car is associated with tile number 9, 10, 15, and 16 in camera 1, and the other objects associated tiles are also shown as follows. As we profile the reality results over time, we will get a lookup table as follows. So this lookup table will record all the objects appeared on a given time step and all their associated appearances, expressed using camera tiles. This lookup table resembles all the cross-camera data association. So based on the lookup table, we can establish a combinatorial optimization problem to generate the optimized ROI mask. I will not show the mathematical expression here, but the intuition of the optimization problem is that to select the minimum number of the tiles among cameras such that every object in this field could be observed by at least one camera in any timestamp. And the following figure shows a solution if we only consider the two cameras on a single timestamp. That is, if we only consider camera C1 and C2 on timestamp T1, we will get a solution as our right boxes shows. We can only keep the right tiles and remove all the other blanking tiles. And by doing this with this solution, we can still keep that every vehicle is still detected at least once through these two cameras. Okay, so the following 5 figures present the ROI mask solution if we apply this algorithm on 5 cameras over profiling of 1 minute videos. As you can see, 58% of video contents are removed, and thus a significant portion of communication and computational costs can be reduced. And finally, we would like to show the evaluation results of our work. We evaluate our system over the real-world traffic video feeds, which is the NVIDIA NICT challenge dataset. This dataset consists of 5 synchronized videos located at a traffic crossing. The video is 3 minutes long. We use the first 1 minute as offline video feeds for CrossRoI to learn the cross-camera correlation, and the last 2 minutes for evaluation. We compare CrossRoI with baseline and no filter design on unique vehicle detection tasks. The no filter design is a CrossRoI system without the statistical filters and directly applies the raw reality data. As you can see from the figures, CrossRoI reduces 42% of network overhead and 25% of end-to-end delay, while keeping more than 99% percentage of detection accuracy when compared to the baseline method. We also compare CrossRoI with one of the state-of-the-art video analytics system, the Reducto system. As shown in the table, CrossRoI can reduce more network overhead and end-to-end latency compared to the Reducto system. So that's the end of my presentation today. Please let me know if you have any questions.